A very good afternoon to all of you.
Good afternoon, sir.
So today we are going to discuss about course code BMTC-132 and course title is differential equation. Am I audible?
Yes, sir.
So now let us see the course outline of this block number 1. So today our main focus is to discuss about block number 1. In block number we have to cover this 5 unit number 1 to unit number 5. And as you can see in first unit, we have to cover about the R square and RQ. R square is about the two-dimensional system and RQ means three-dimensional system. So in R square, in two-dimensional system, we have to represent. So it is R square is a set containing all the points that can be represented in order pair form. And in RQ, that is in three dimension, all the points must be in three dimension, that is, that can be represented in triplet form, that is x, y, and z. Each variables will contribute each real numbers, that means r cross r cross r. Also can be present r cross r means there is a Cartesian product of three set of real numbers, that is RQ, and Cartesian product of two set of real numbers is R square. So two dimensional systems and three dimensional systems. So basics about the two-dimensional system and three-dimensional systems are discussed in the previous course, that is BMTC-131, and here we are going to discuss about the functions, how we can define functions in this R square and R cube. Then we are using this function in unit 2. We are going to calculate the function value, its limiting value, continuity, and partial derivatives, and we are going to discuss about the differentiability of a function. So gradually we discuss one by one. So let us begin with the function in R square and R cube. That means how we can represent, how the functions look like when we define it in R square and in R cube. And we are moving towards the page number 4040, and in that phase the definitions and basic idea about the functions in two variables and three variables are given. So we are moving towards page number 40. So here in page number 40 you can see functions from R to the power n to R. So here domain of the function will be R to the power n, and as we are restricted to n must be equal to 2 or 3, because we are going to define a function from R square to R or R cube to R. So these functions are known as real valued functions of three variables or two variables. If we are defining a function over R square, then that is a real valued function of two variables. If we are defining the same in R cube, then these are known as real valued functions of three variables. So as you can see in the definition here, in definition 11, here we have taken a function f of three variables. So the rule to define the function is that the domain is a RQ set and codomain is a R set, and we can define the output of the point xyz in the form of f of xyz. So here xyz is the triplet point that is taken from R cube, and once we get the output given by the function, that will be represented in set of real number R. So in this way you can define also f is a function from R cube to R by using arrow mark symbol. And similarly here, in the second form of function for two variables also defined in the form of f is a function from R square to R. So here R square is the domain and R is the codomain of the function. And generally we represent in the form of f of xy. That means here xy is the input point or the input taken from the set R square. in order pair form. So that's why this is known as function, real valued function of two variable. Now let us look at some basic fact about these two-dimensional and three-dimensional functions in set of real number. So here in note number 1, we have to focus that a function of three variables means that the domain of the function is a subset of Rq. So it is always true that the domain must be a subset of Rq, or it will be itself the set Rq. So similarly, you can also define, so whenever the domain will be the subset of R square or R square itself, these functions are said to be a really valued function over two variables. Now look at the second point. In second point, the real valued function means that the range of the function is a subset of R. And similarly, the real valued function of three variable also gives us a single result of real number R. So that's why both the real valued function of two variable and three variable both are said to be real valued function, and that is a subset of R. That means the output of the subset set of real number R. And we have given some examples to define the function here. Look at the first example. In first example, the input set is R square, and the function is defined like that: f of xy equals to sin x plus sin y. Madhusmita, hello.
Sorry, good afternoon,
Do you have any question?
sir. I'm just joining the meeting.
Okay. Please mute your mic. Okay, thank you. So let us move to the second example, and that example is defined over the set of Rq in three variable system. So here, if the function of three variable x, y, z, and the function is defined in the form of under root 1 minus x square minus y square minus z square. So these are the simple form how we can define the function in two variables and the functions in three variables. And look at these outputs. Maybe from the first example I, or maybe from the second example I, the result of this function will give us a single value. So that's why these functions are known as real valued function, and the range set must be a subset of set of real number R. So in this way, we can define the functions over R square and R cube. Now we can also define some implicit functions. So look at that implicit function. That means x, y, z directly not given by the function inside the function f, but we can represent in the form of z is a function of x, y. So it is also, you get the expression z equal to f of x, y. So this is also a function of three variable, and here we can represent capital F the function of three variables x, y, and z. But here z is given implicitly, and that is given z equal to f of x, y. So here the function capital F is known as implicit function, but small z equal to f of x, y is known as explicit function, and that is defined over the function small f. So these are the simple forms to represent the function in R square and R cube and the implicit functions. Now similarly, we can plot the graph of two variable function and three variable function. So now look at the first graph that was defined in figure A. In figure A, that is a graph we have drawn for the function one variable, and in figure B, that is the graph of the function in two variables. That means whenever we are taking two variables from a system or from subset of R square, we have a certain region, and if we are using the value from that region, we have a set of outputs, and if we are going to draw in a figure this output result, then that will be again another region. So look at that. So diff blue, this region is the output, and the shadow is the input of the function. So here the definition goes like that. Definition 12. So here we have taken a function of two variable and the domain is Z. Then the function, then the graph of f is denoted by g. So whenever we're going to draw the graph of a function, that particular graph is represented by capital G of f. And here I can say that this graph must have the point in triplet form, that is x, y, z, and here z is a function of again two variable x, y. So here you can see that the function is defined in implicit form. The function is defined in implicit form. So these are the some basic rules to define the function in R square and R cube, and how can draw the graph of these corresponding functions in two-dimensional plane and in two-dimensional plane generally, because the output of all these real value functions of two variable and three variables are in terms of set of real number R. So now let us moving towards the limit and continuity of this function, this kind of functions. That means how we can calculate if the function contains two variable or three variable. That means calculation procedure and definition of limit of this kind of real world function of two and three variables. So till now, if you have any doubt, then please. Otherwise, we are moving towards the page number 55 to discuss about the limiting process or calculation procedure of these limits. Any question? Any questions from anyone, sir? Anyone? So here, limit and continuity. So this is the second unit of this particular discussion or counseling session. The outline of the unit is like that. First, we have to discuss the limit of real valued function. Then we are using the definition of continuity. Then we are discussing the repeated limits, and then we are going to discuss the relation between repeated limits and simultaneous limit of a function of two variables. So basically, we are now restricted our discussion about a function of two variables. That means all the limiting conditions and continuity conditions will be discussed over a function that containing exactly two variables. So here, let us see how we can define a function or limit of a function of two variables. So the definition is quite similar to the definition that we discussed in the course BMTC-131. And look at the expression. So here, in the same way, we have taken a function that is a real valued function over a single variable x. So that is the definition given for a single variable x. But that particular definition can be approached to function of two variable and three variable as well. So let us see. So whenever we are using limit in a function of single variable, we just write x approaches to a point x naught or a or b, just like that. But when we are using limit for a function of more than one variable or exactly two variable, we have to represent like that x comma y approaches to 0, 0. That means when x approaches to 0 and y approaches to 0, simultaneously both are approaching to 0. Look at this function. These functions are defined fxy when xy not equal to 0 and gxy when xy not equal to 0. But look at the formal definition. That means how we mathematically represent the limit of a function for two variable function. So here look at the expression. So here the function is given like that. So f of xy approaches to L. So here L or capital L is the limit of the function f. But condition is that when or as the point xy approaches to the point AB. And now, according to the formal notation or mathematically, we can represent that one limit, that is LIN. And look at the bottom of that word limit. You represent here xy, then arrow mark AB. That means when the point xy approaches to the point AB, then the function will attain a value or a real value, that is L. So in this way, double limit, or you can say that a function with double variable can be represented in the form of a limit. So now let us begin the definition. Definition or the classical approach or the epsilon delta definition of limit for a function of two variables. As we know, in function of single variable, when we using the epsilon delta definition, we are using here x approaches to a, that means the difference between x and a will be small delta, then the difference between the function and its limit will be less than epsilon. So that particular definition will be used here. Now look at here. Whenever x approaches to a and y approaches to b, these 2 points, xy is the point present in R square, AB is also the point present in R square. So whenever we are going to find out the distance between 2 points in R square or R cube, we are using this kind of symbol. That means a pair of double vertical lines. So look at this expression, that is also known as norm of x and y. That means the difference between 2 points x and y, that is the norm of the point x and y in R square, and it will be calculated like that, root over of x1 minus y1 square, that means difference between the first component, plus square of difference between the second component of these 2 points. So this is the distance formula we are using here in terms of norm of 2 points x and y. And similarly, if we are dealing with the third dimension or three-dimensional system or R cube, then one extra component will be added, that is x3. So here two basic representations are exactly the same in R square and R cube, but in R cube we have to add one more extra component, that is square of the difference of third component, that is x3 minus y3 square. So this is the simple representation or simple formula to calculate the distance between 2 points in R cube or in R square or higher power of capital R or set of real number R. So on the basis of this representation, we can define the distance between 2 points by using the representation norm, and that will be represented by a pair of double vertical lines, like are written here in the particular box, highlighted here in the particular box. So now let us discuss about B, capital B AH. So that will define a ball, that is open ball containing the point A, and the radius of that particular ball is h, and that will be represented here. So whenever we find this representation capital BAH, so that is a ball, center is at A and radius is h, and that will be represented by like that, a norm of x minus a less than h. So h may be positive, which is greater than 0, because that will define the radius of that particular ball, and that particular ball will be called as the neighborhood of a point, or we can simply represent h neighborhood of the point A. So this particular definitions and representations are very much necessary to define the definition of limit of a function of two variables, and the definition is represented in definition number 2. So look at the definition number 2. Definition number 2. This one. So here, in the same way, we have taken f, that is a real valued function, and the function is defined over a set. So here this is a ball or open ball that is also containing a set, that is a subset of Rn or R to the power n, that is n equal to here 2 or 3 according to our requirement, that means 2-dimensional or 3-dimensional. Now look at the definition of a limit when we are dealing with more than 2 or 3 set of real number R. So that has been written like that. For every given epsilon greater than 0, there exists a positive real number small delta that is depending on epsilon, and small delta is less than h. So here h is the radius of the ball that was discussed earlier in the neighborhood of the point, and that has been summarized here. So look at here, norm of the point x and a will be greater than 0 but less than small delta. Then we can say that the difference between the function f and L will be definitely less than epsilon. So this is the formal definition of the limit of a function at a point A. So now we are going to discuss a small example how we can calculate the limit of a function when we have two variable or three variable function. So now before I want to discuss about the calculation procedure, let us see the geometrical meaning of this limiting calculation procedure. So now before I want to discuss, let me to ask you if you have any question, then please. Do you have any question? Okay, very good. So let us move to the figure that was you can see in figure number 1. In first A, the first figure shows the values of x, y in R square, and that is sufficiently close to R. That means, as we have in the definition we have mentioned here, the difference between two points. So x is the point having coordinate x comma y, a is the point having coordinate a comma b. So whenever these 2 points are very close to each other, then you can say that their norm value x minus a norm will be less than small delta. So here in this picture you can clearly see that small delta is the radius of that particular set in a circle, and the circle is a ball that is known as capital BAH. So in this way you can define the definition of the limit of the function. So now let us know the calculation procedure. So now look at the algebra of limits. So in algebra of limits, this particular simple expression formula algebra are well known to us in the previous course, that is BMTC-131. So here we have stated like that, let f and g be two real valued functions that are defined in a deleted neighborhood of a point A in R to the power n, that means n equal to 2 or 3, then limit of f of x at a equal to L and limit of g of x at x equal to a equal to m. Then the following condition holds. That means if a scalar is multiplied with a function, then if you are going to calculate the limiting value, then alpha can be taken out of the limit because it is a constant, and limit of function is L, so we can represent alpha into L. And here you can say that sum or subtraction of any two function, and limit will be taken over the same point, then we can represent sum or subtraction of limit of the corresponding functions, we can say. In same way, you can also see the limit of product of two functions, and limit of quotient of two functions can be represented as well. But here in the last one, condition is that the denominator, that is the value of m, should not be 0 here, because if the value of m will be 0, the result will be undefined, and that is not justified. So that's why the same definition now, the definition that I discussed earlier in R square is now represented in R cube. So now after discussing all the definition, now if you have any question, then please ask me. Otherwise, we are going to discuss about their calculation procedure. Have you any question? No. Very good. Then let us move to the page number 61. So look at the box highlighted here in bold alphabets. So here that is a note we have to keep in always mind that. So let us first discuss about the remark. So whenever you're going to calculate the limit of a function having two variables, we have to represent like that limit xy approaches to a b f of xy exists and equal to L. Then you can say that the function f of xy approaches to L is the point xy approaches to the point AB along any path. So that means it is path independent because these points xy and the point AB is lies in a particular plane and we can move through any path from the point xy to the point AB if limit exists. That means if limit exists, the limit will be path independent. So that should be keep in mind when we want to calculate the limit of the function. Now let us look at the condition that was highlighted in bold alphabet. So here we have to keep in mind that if a function f of xy tends to two different limits when xy approaches to AB along two different paths, then limit does not exist. So that was again highlighted here. That means we have discussed that whenever limit of a function exists in two variable, then we can say that the point approaches from one point to another point, it is path independent. But if we have more than one limiting value for different path, then limit does not exist. So that is the main summary of this Photoshop discussion in this particular section, and let us look at about the corollary. So here look at the function real world function f of xy, and here it was defined like that if there exist real world functions phi1 and phi2 such that limit of phi1 at a equal to b also limit of phi2 at a equal to b. Now limit of f of x phi1 not equal to limit of x f of phi2. That means so then a limit does not exist. Though the values of the limiting value of phi1 and phi2 at the point A is exist and equal, that is same, but f of x phi1 not equal to the limiting value of f of x phi2. If those are exist but not equal, then conclusion will be made that the limiting value of the function at the point AB does not exist. So this corollary is very much useful when we are going to solve problems of exercise or examples given below. So now let us move to the calculation procedure. So here we have to show that in example number 3, we have to show that the function does not exist or the limits of the function does not exist when xy approaches to 0. Look at the first function. Here the first function is f of xy equal to x square minus y square divided by x square plus y square. So as it is not given the path of calculating the limiting process or limiting value, so that's why by default we have chosen here a path, and that path is a straight line in the form of y equal to mx plus c. So that is the path we are choosing to move from the point xy to the point 0, 0 or origin. So that's why we substitute the value of y in the given function, and after substituting the value of y as mx in the given function, then very soon it will be converted to a function of single variable x, and here x will be approaches to 0. So now after taking x square common from the numerator and x square common from the denominator, we have the result 1 minus m square in the numerator and 1 plus m square in the denominator. But the result or the output is not unique because m is any value. Any value means any real number. So if we are using different value of m, then we get the different result in the right hand side. That means m equal to 1, we have one result. If we are using m equal to 2, the result will be different. Similarly, if we are using different values of m, we get different value of the result of the limit. So that's why we can say that the limit of the function does not exist when xy approaches to 0. And the conclusion has been given according to the corollary that was discussed earlier in this session. And the same process has been adopted. That means again in the example number 4, as you can see, the path has been taken y equal to mx, that is straight line, and the straight line from xy point is the initial point, and 0 point will be the final point of this path of limiting calculation procedure for that function f. So the same process of calculation has been used to calculate the limit of a function for more than one variable, that is for two variable and three variable as well. So now again I am going to ask you, if you have any question, then please. Otherwise, we are moving towards the next section, that is all about the continuity of a real valued functions. So have you any question? Nikunja Bihari? Can you hear me? Am I audible? So let us move to the section continuity of a real valued function. Here, as we have discussed, the definition of continuity of a function in single variable, that was also given for our reference, and the definition was like that: a function f or single variable function f is said to be continuous at a point if this condition is satisfied. That means if the limiting value of the function is equals to the functional value, on the left hand side it is limiting value of the function at x equal to a, and in the right hand side that is the functional value at x equal to. So we can say that limiting value will be equal to the functional value, then we can say that it is continuous at that point. So same idea is now extended in the function of two variable or three variable, that means r square or r cube. And it is represented like that. In other words, a function f is continuous at a point ab. This expression limit xy equals to ab, function of xy equals to function of a. That means the left hand side of the limiting value must be equal to the right hand side of the functional value at the point ab. Then we can say that the function is continuous at the point ab. Also, the same condition can be summarized into different points. That means first condition is if f is defined, well defined at the point AB, that means the functional value exists, as well as we are able to calculate the limiting value, and if both are exactly equal, that means the limiting value and functional value both are equal, then we can say that the function is continuous at the point AB. Look at the note number 1 and note number 2. So if we are looking at note number 1, so here the condition number 2 indicates not only the limit exists, but also it is equals to the functional value f of AB. F of AB. So the single mathematical expression has been written in two different sub point I and 2i, but it is better to remember that particular formula or representation to define the continuity of a function at a point AB. So now let us define and let us want to discuss the definition of continuity of a function at the point origin at 0, 0. So look at the first function. As we have discussed earlier in the previous example, the limit of the function x square minus y square divided by x square plus y square at the point is 0, 0. And we have found the output is that the limit of the function does not exist. So if the limit of the function does not exist, then we clearly give the conclusion that f is not continuous at the point 0, 0. And also we can notice here the function is not defined in the point 0, 0. Because if we are going to substitute the point x equal to 0 and y equal to 0, then numerator will be 0 and denominator will be also 0. So that's what in that condition 0 by 0, that is indeterminate form condition, the function is undefined. So if any one is undefined, then we can say that the function is not continuous at that particular point. So the same definition can be used to test whether a function is continuous at a certain point or not. Now let us focus on the next definition, and the definition is all about the continuous function in a set. So the definition 4 gives us an idea about the continuity of a real valued function on a set A containing the domain of the function. That means the condition is that if the function is continuous, if the function is continuous at every point, each point of its domain, then we can say that the function is a continuous function, and we can say that it is continuous at every point of its domain of the definition. So according to that particular idea, we can extend our result with the help of this continuous function. So that is theorem number 5, that is gives us the idea between algebra of continuous functions. So here the statement is like that: let f and g be two real valued functions of n variables. So here n must be restricted to 2 or 3, which are continuous at a point. So if a is a function continuous at point A, g is a function continuous at point A, then their addition and subtraction is also continuous at the same point. Scalar multiplication with a function is also continuous at the same point. Product or multiplication of two functions also continuous at the same point. Also the division or the quotient of the function is also continuous at the same point. But condition is that the denominator should not be 0. That means g of a should not be a 0. So these are the simple basic rules in the algebra of continuity of a function in a particular point or in a particular interval or in its domain. So now let us move towards the repeated repeated limits of the function at a certain point. That means how we can calculate the repeated limit of a function, and that will be given in page number 70. So let us move to the page number 70. So I am covering the important and basic features of this particular block 1, containing exactly 3 units, unit number 1, 2 and 3. So let us move to page number 70. Repeated limits. So first let us look at the difference between the previous limit that was written and the limit that was written here in this particular section, that is the main focus point of discussion. Look at the expression here. So in previous expression, the limit is represented in a single time. That means under limit, we have directly represent earlier x comma y arrow mark then a comma b. That means the point xy approaches to the point a b. But here, look at the difference. Here, first we represent inside bracket limit y approaches to b function of xy, then limit x approaches to a outside of the bracket. So here, the meaning is that first we have to calculate the limit of the function with respect to when y approaches to b by treating as x is constant. Then finally, after calculating the inner side of the integration inside the bracket, we have to calculate the limit after when x approaches to a. So that's why this is known as a repeated limits. We are repeating the calculation procedure limit twice. We are repeating the process twice, first for the variable y and then for the variable x. Or in other words, we can say that first we can calculate for x or then we can calculate for y. That's why this is known as a repeated limit and expressed in that form. So basic difference of limit and repeated limit is that in repeated limit we are calculating the limit of the function one after another variable. But in limiting process we can calculate directly from xy to ab. So look at the expression here. So here the initial point is xy and the final destination point is ab, and we have to calculate the limit of the function when xy approaches to the point ab. So according to the figure, we have taken two paths. First part is P1 and second path is P2. So if we are going to calculate the limit with respect to path 1 and with respect to path 2, if both are exist and both are equal, then we can say that yes, the limit of the function exists and equal to that particular value. But in case if any one of these value are not equal to the other one, that means the value of the limit of the function with respect to the path 1 is not equal to the value of the limit of the function with respect to path 2. Then we can say that the limit of the function does not exist at that particular limit. So here, this is the formal definition that we have discussed. Now, look at the example. In example number 10, that was given us to calculate the repeated limits of the function xy given in the form of whole square of x minus y divided by x square plus y square. So repeated limit means, look at the expression, x approaches to 0 outside of the bracket and y approaches to 0 outside of the bracket. That means these two possibilities are there. Then if both are equal, then we can say that the simultaneous limit does not exist. So here you have to show these results. The repeated limits are exist and equal, but the simultaneous limit f of xy does not exist. So look at here. So clearly, if you are going to calculate the limit x tends to 0, function value is 1, then y tends to 0, function value is 1. So repeated limits both are exist and equal to 1. But if we are going to calculate the simultaneous limit, the derivative that was calculated earlier in the form of x comma y approaches to a comma b, that is known as simultaneous limit. And in that simultaneous limit, we have to choose a path. And very simply or generally, basically, we are checking a path in the form of y into mx, a straight line direct from xy to the point ab. So after substituting y equal to mx in the given function, then we are taking limit x approaches to that particular point a or b, or it is given here 0, 0. Then the value will be different for different value of n. So that's why limiting value does not exist. So here, one thing is clear that the existence of the repeated limit does not imply that simultaneous limit is also exist. So that's what we can, and that has been discussed in this particular example, example number 10. And this type of examples are given, and the same has been repeated here in this theorem number 7. So if the repeated limit exists, if both are exist and equal, then we can say that the value or the real valued function must have the limiting value L. So now, till now, if you have any question, then please ask me. Otherwise, we are moving towards the next part, that is all about the first order partial derivatives and its definition. First order partial derivatives and its definition. So let us move toward the definition of first order partial derivative, that is in the page number 81. So let us move to the page number 81. 81. So in page number 81, look at the definition of one here. And the definition is for the partial derivative of the function of two variables x and y with respect to the variable x. So that has been represented like that. So f subscript x, that means there is a partial derivative with respect to x. So that's why here in the function we represent x plus x comma y minus f of x. So that means here the value of x is changes, x plus h and x. So that's why the result will be represented in the form of first derivative of f with respect to x, and this f subscript x has been written. Similarly, if we are going to calculate the partial derivative with respect to y, then we represent f subscript y, and limit will be k approaches to 0, and look at the difference here, it is x comma y plus k minus f of xy divided by k. But earlier previously we have represent x plus h comma y, but in the second we have represent x comma y plus. That means in the second definition y changes, or we are going to calculate or estimate the change in y, but in first definition we are going to calculate the change in x. That's why that is rate of change in the direction of x, that is partial derivative with respect to x. And if we are going to estimate the rate of change in the direction of y, that is the partial derivative of the function with respect to the direction y, that is represent f subscript y. So these are the basic definitions and notations given in this textbook. And the partial derivative with respect to x can be represented in different form, f subscript x, or also we can represent capital D1. So capital D1 is understood that that is partial derivative with respect to first variable, whatever it may be. And the third one is del f by del s. Similarly, partial derivative of y can be represent fy or d2. d2 means it is always understood that partial derivative with respect to the second variable, whatever it may be. Similarly, del f by del y. So this particular expressions are generally used in the section of partial derivative of a function of more than one variable. So generally these partial differentiations are useful in one variable or two variable, two variable or three variable. So here the same definition has been extended to the function of three variable, that is f of x, f of y, and f of z. In f of x, look at the expression x is changes, x plus p, and here this is x. Other two variables are exactly same. Similarly, in fy, increment of y is to be estimated, y plus q minus this is y. Other two variables are exactly same. Similarly, in fz, z change of z, that means z plus r minus z, and other two variables are exactly same. So these are the simple definition to calculate the partial derivative with respect to x. and with respect to y in terms of two variable and three variable. So let us now going to discuss with the help of this example number one, that is supposed to calculate the derivative of the function with respect to two variable, that is x comma y. Have you any question? So now let us look at the question, that is example number one. So here f is a function defined over r square to r, and the function is defined like that, that is a polynomial into variable x square plus xy plus y cube, polynomial into variable. So we have to calculate here fx, partial derivative with respect to x and partial derivative with respect to y. And according to the definition, we can represent here x plus h comma y and xy. So the function has been written according to the variables x plus h comma y, this expression, and after algebraic calculation, we cancel the term of x square, y cube, and xy. After cancelling these terms, we have the expression 2x plus h plus y. And here h will be approaches to 0, that means h will be 0, and the result will be 2x plus y is the result of partial derivative of x, f with respect to x. So the same process will be used to calculate the derivative of other variables. So calculation procedure of first derivative of function with respect to x and with respect to y. Now the same will be defined in the form of differentiable. That means now differentiability of a function of two variable can be defined in the form of partial derivative. So now these definitions and basic idea can be used to define the differentiability of a function of two variable or more than two variable. And the definition is given in the page number 97. So let us move to the page number 97. As we have few times left, so let us going to discuss about the same in page number 97. So this is the differentiability of a function from, that is defined from r square to r. So the definition is represented here, but look at the definition, main definition of differentiability of a function. So here the definition goes like that: f be a real valid function defined in a neighborhood capital A and of a point, and then the function f is said to be differentiable at the point AB if the following condition holds. So let us focus about the condition, and here the condition is that f of a plus h comma b plus a minus ab. So now look at the left hand side of the expression, that is the difference between the functional value at AB and at a plus h and b plus h. That means we are calculating the increment or the change in both the direction x as well as y. But in our previous discussion, as you calculate the first derivative with respect to x, that is partial derivative with respect to x, we are focusing in a single direction, or partial derivative with respect to y, we are focusing in a single direction. But if we are going to calculate the derivative or rate of change or changes in both the directions simultaneously, then that is coming under the differentiability of a function at a certain point. And here it can be represented like that: capital AH plus capital BK plus AH pi HK A psi HK. So these are the some constants and functions defined newly, and let us focus on these numbers. So here h and k are the real number, and they will use to define the point that is very close or near to the point AB, and that is the new point is a plus h comma b plus h. And now capital A and capital B are the constant, These are independent of h and k. That means these are the independent of small increment with respect to h and k. But depend on the function f at the point. So the value of capital A and capital B are dependent with respect to the function, with respect to the point, but it is independent with respect to h and k, small increment in x-axis and y-axis as well. And finally, the two functions phi and psi are the function tending to 0 when hk approaches to 0. When hk approaches to 0, the function will be automatically tending to 0. That means if a function is differentiable, then its differential value will be h plus bh when hk approaches to 0. And the same has been discussed in the following example. So here in this example, as you can see, the function is taken x square plus y square, a polynomial into variable x and y. We have to show that it is differentiable at the point AB. So same definition has been adopted here: f of a plus h comma b plus a minus f of AB. And according to the function, we have calculated the value is 2h plus 2bk plus hx plus kk. Now, if we set capital A equal to 2a, capital B equal to 2b, phi function is h, small psi function is k. So the meaning of expression of this h, and k is that we have to take in the other h as a function of phi and k as a function of psi. So that's why after taking or setting these new variables and constant, the function will be looks like that. Then where a and b are the constant that are independent of h and k. Now the function will be approaches to 0 when hk approaches to 0, and the value of the function will be now, and set the conclusion will be clearly the function is differentiable at that point. Condition is that the function phi and psi must be approaches to 0 when hk approaches to 0. So this is the limiting condition of the function at the point hk. When they approaches to 0, the result will be 0. In that case, you can say that yes, the function is differentiable at the point a, b. So these are the fact about the differentiability of a function at a certain point when it is a function of two variable or three variable, or you can say that more than one variable. So again, I request if you have any question, then please ask me, otherwise we are going to end the session. Ritika, have any question?
Sure.
So have you your textbook?
Sure.
Do you have your textbook? The given test that is
Yes, sir, I
BMTC
have.
131. So whatever discussed we have in this session, please go through each and every article and practice on your own. If you have any doubt, then that will be discussed later in the second session. Now, Priyanka, if you have any
Okay,
doubt,
sir.
okay, thank you. Ritika, please put up your mic. Hello, Priyanka, do you have any question? Otherwise, you are going to end the session. Hello. Hello. Sorry, I cannot hear you. Your voice is not audible. It is a rattling sound. So, okay, thank you. So, whatever the doubts you have, that we will discuss in the next session. So, today we are going to end the session, and I hope please go through your textbook and go through whatever the section discussed earlier in this session. So, thank you very much. So, now we are going to end the session.
Yes. sir. Thank you, sir.
Okay, thank you.
Thank you, sir.